Hereby I open this academic ceremony in which Andrea Calore will define the academic thesis. I also would like to welcome first the supervisors of this thesis, Professor Moroni, Dr. Jules Harings, Dr. Katrien Bernards, and Dr. Carlos Motta. I also would like to welcome family and friends, colleagues of Andrea Calore. So I would now like to invite you to present a summary of your study on fantastic prints and where to find them, processing routes for 3D scaffolds in tissue engineering, and the conclusions of your thesis.
Thank you, Prorector, for the introduction. So my name is Andrea Calore, and I welcome everybody, I welcome you all to the defense of my thesis titled Fantastic Prints and Where to Find Them, Processing Routes for 3D Scaffolds in Tissue Engineering. The focus of my thesis is melt extrusion additive manufacturing for bone tissue engineering. But what is tissue engineering? Tissue engineering is a discipline that aims at providing organs and tissue substitutes to patients starting from their own cells. And these are then made grown in vitro. In this process, an extremely important role is played by 3D scaffolds that are 3D structures that aim at providing support and a familiar environment to cells during growth in the lab. Scaffolds can be and have been manufactured via several techniques over the years, but lately the so-called 3D printing class has emerged as a golden standard. In particular, one subclass called melt extrusion additive manufacturing has been successfully employed for hard tissue regeneration by melting and depositing thermoplastic polymers. The main reasons for the success of such class of manufacturing techniques derive mainly from the control over scaffold morphology to the layer-by-layer manner of deposition during manufacturing. And this control allows the production of personalized implants with, hopefully, the desired morphology and mechanical properties. In addition, the relatively low manufacturing costs, but also the possibility to automate production, has further pushed the general adoption of this class of techniques. However, the road is still long. A few drawbacks are still present in the current workflow for proper implant production. A few of these are, for example, the present that is still there of manufacturing inaccuracies that might lead to suboptimal mechanics, but also the need for post-manufacturing steps to make scaffolds be liked more by cells, the general brittle behavior of the implants produced, the fact that a few materials do not go very well with the temperatures involved in manufacturing and therefore they lose their chemical integrity, and also a few other processes that usually tissue engineers do not account for, such as crystallization and smooth surfaces. Therefore, the challenge is to manufacture scaffold in a precise manner with the desired and optimized performances eventually in the biological environment. And this challenge was tackled through the chapter of this thesis. We started with chapter 2, where we decided to develop a mathematical model of the scaffold printing process to allow for the fully controlled production of standardized products, but mainly with the desired properties. So not having this process being random and not adopting a trial and error loop to obtain scaffolds with the desired properties. First, we started by understanding the actual variables describing the material dispensing process, and afterwards how these affect scaffold properties such as the morphology and therefore the cross-section of the fiber making the scaffold, the mechanics, but also the possibility of properly bridging two filaments from the previous layers so that to avoid lateral pore occlusion. That is very important for nutrient flow and waste uptake, for nutrient uptake and waste flow. Then we moved on to understanding the complex interplay between these variables and with each other. And as you can see, it's a quite dense and quite tricky loop. It's a very dense loop where a small change in one of these variables might affect all the others, and therefore production has been never straightforward so far. Eventually, we managed to derive the equations describing the evolution of every variable. And noteworthy is the key role played by temperature, which is correlated to every variable. We then notice that the actual input parameters of our model are nothing but the characteristics of the printer in light blue, and the material properties in purple. Why is this important to mention? Because both can be easily obtained. So machine features can be obtained by the machine datasheet, while instead material properties can be derived by two easy tests, differential scanning calorimetry and rheometry. Therefore, the moment we have the input variables, our model just works as a black box, so you don't have to get scared if you see all those equations. They are all inside a black box that you don't see, whose content you don't see from the outside. And basically, after we input this black box, these parameters, machine features, and material properties, the model allows to first understand if a material can be printed, can be manufactured with a specific device, and then how to do so to obtain an accurate morphology, but also the desired mechanical properties. We then moved on trying to tackle other issues affecting the workflow of scaffold production. In chapter 3 in particular, we focused on the tendency of some materials to lose their molecular integrity during printing because of the presence of high temperatures, but also on the inherent bioinertness of the synthetic polymers used. In fact, unlike biological polymers, this material usually lack the physical or chemical cues that drive cell fate in vitro in vivo or in vitro with the use of biological materials. Cells, therefore, usually don't get out of their chilling state, and they stay there without doing what we actually want. Generally, these issues have been solved by the use of stabilizers that often are toxic chemical compounds, while instead bioinertness have been tackled by the use of post-manufacturing steps, making, however, the workflow much longer than we would like to have. Instead, in chapter 2, we used vitamin D3 to kill two birds with one stone and to use it as bioactive plasticizer. But why bioactive plasticizer? Plasticizer because instead of solving the problem of thermal degradation and loss of chemical integrity, molecular integrity, as stabilizers would do, we instead just want to avoid the degradation process by plasticizing our material. The plasticization effect does nothing but reducing the viscosity of the material. This allows processing the material with a lower torque requirement, so with a lower driving force. Instead, so far, to compensate for higher viscosities, tissue engineers would just raise the temperature, which is the main factor driving thermal degradation. By applying this strategy, we can do nothing but decreasing the manufacturing temperature and therefore slowing down degradation. Interestingly, this came at very little expense of mechanical moduli, as you can see from the graph. The second function of bioactivity results from the fact that the inclusion of vitamin D3 had the effect of promoting osteogenesis and mineralization in vitro, as you can see by the enhanced secretion of osteogenic related protein at 7 and 35 days of cell culture, but also indeed, as you can see from the graph of the release from the alizanin red assay, that basically states the amount of mineralized materials deposited by the cells during the osteogenic studies. My apologies. We then moved on to chapter 4, and in this chapter we worked on making scaffolds more similar to the spongy area of bones, a zone that is characterized by the presence of multi-level porosity, where instead the usual scaffold manufactured via 3D printing show only the so-called macroporosity, that is the porosity deriving from the deposition pattern. Why did we work on this topic? Because microporosity to spongy bone grants in spongy bones grants ductile behavior and rough surfaces, where instead traditional scaffolds are usually rather smooth surfaces and have relatively brittle behavior. And with particular focus on smooth surfaces, we know that are not very much appreciated by cells, at least bone cells. Then, considering that I'm Italian, when developing the strategy to solve this issue, the idea came from food, in particular from cakes. We use sodium citrate, commonly known as baking soda, to mix it with our main material, our main polymer, together also with a water leachable agent. So briefly, after mixing all these materials, during printing of the scaffolds, upon the application of heat, sodium citrate, baking soda, would just form, forming all the pores you see inside cakes and inside our scaffolds as well. Eventually, after incubation in water, the water leachable phase would just be released from our scaffold, allowing the interconnection of the pores internal of our fibers, but also the opening of these pores to the outside, so effectively creating an interconnected network that is also open and accessible from the outside. As you can see here from electronic microscope, we can see here that we managed to obtain rough surfaces, but also internal porosity. So here you see rough surfaces, here you see a cross-section of a scaffold, and down here you see a pore. On the right, we conducted a micro-CT analysis, and you can see in green all the pores that we originated via this structure. On the image below, you can see a longitudinal cross-section of a fiber making the scaffold, where you see that the porosity develops all along the fiber itself. And on the bottom, you see a detail of a pore. And here, a video of a reconstruction from the micro-CT images, where you can actually see that there's a pore open to the outside, and you can effectively travel inside it along the fiber without actually passing any wall. Interestingly, microporosity led also to a more ductile behavior where compared to scaffolds with no microporosity at all, without having, and that was a worry we had at the very beginning, without having significant differences in modulus, meaning that the scaffolds mechanically, in terms of elasticity, they performed the same. Moving on, attachment studies showed the greater amount of adhering cells when comparing to scaffolds with no microporosity and pre-treated the usual way to promote cell attachment. In addition, we noticed a difference. We noticed a more spread morphology on scaffolds manufactured via our strategy, and we know that the morphology of cells has a strong impact on their commitment to the osteogenic lineage. This was in fact further confirmed by longer cell studies where we noticed an increased secretion of proteins related to the osteogenic lineage. Eventually, in chapter 5, we proceeded at investigating if cell fate is somehow influenced by plain material properties. So far, we have been working with modifications to our materials. In this case, we wanted to understand if by just using our plain materials, we could somehow trigger something in cells. This was done by basically influencing surface stiffness and roughness via the formation of crystallinity, which is a property that spontaneously develops during printing upon cooling from the melt. Why did we do this? In most of the cases, the development of crystallinity and its potential effect on cell fate is generally unaccounted for by tissue engineers. Therefore, we wanted to evaluate if, by printing our scaffolds with synthetic, thermoplastic, semi-crystalline materials, we might somehow give a priming effect to cells cultured on these materials and therefore somehow make them commit already to a certain lineage. Considering that surface stiffness and roughness are strongly intertwined via the formation of crystals, we developed a strategy to separate the two properties. We include the plasticizer, another plasticizer, vitamin E, in our main material, and we applied thermal histories typical of 3D printing process to films made with this blend. We managed therefore to obtain two types of films. The first type exhibited varying surface stiffness, but with constant roughness between the conditions. On top of these films, then we moved on and we cultured cells that did not apparently exhibit any preferential commitment to osteogenesis. Therefore, the stiffnesses obtained apparently didn't seem to have any impact on cell commitment to the osteogenic lineage. The same approach was, of course, used to maintain the stiffness constant and allow roughness to vary spontaneously during the processing. This way, we obtain films with comparable stiffness and roughness that freely developed during the processing. As you can see from the graph D, we obtain films with comparable, with no statistical differences in average. However, I think it's important to mention that the standard deviation distribution was very different. Why is this? From cell studies on top of these films, we noticed that cells cultured in osteogenic conditions were more responsive to films that were annealed at the highest temperature and that exhibited the narrowest standard deviation distribution and therefore the narrowest crystal size distribution. And this was particularly interesting, meaning that there is actually a range of roughness that our cells were sensitive for, but they were more sensitive not to the average roughness, but actually to the distribution of the roughness itself. In conclusion, in this thesis, we provided the knowledge to optimize scaffold manufacturing that could allow us to predict scaffold morphological and mechanical properties in order to avoid any time or material waste during processing, especially when working with expensive medical grades. Then we moved on applying this understanding to provide strategies to improve scaffold performance in biological environments, trying to keep the amount of steps needed as low as possible and favor upscaling. In terms of future outlook, I'd like to see one day this model completed with the effect of crystallinity as well, as the model was developed for amorphous polymers, but also to manufacture a multifunctional scaffold encompassing both the role of vitamin D3 and therefore having bioactive effect, but also exhibiting multiscale porosity. Eventually, I'd like also to see scaffold manufactured with gradients either in stiffness or roughness that could help solving the problem of those border regions such as the osteochondral region, where the properties go from cartilage to bone. And with this, I would like to thank you all for the attention, and I give back the word to the prorector.
Thank you, candidate, for your presentation. I would now like to start the opposition, and this will be opened by Professor Kim Ragaard. She was also the chair of the assessment committee. She's a professor in circular plastics here at Maastricht University, and she will be online.
Thank you, Mr. Chairman. Dear candidates, I have greatly enjoyed reading your thesis. Obviously, I have some questions. I have a lot, but I have only 9 minutes, so I will just cut to the chase. I want to start with the model you made in chapter 2. You made it very fluid dynamics based, but as you mentioned yourself, quite often temperature plays a very big role when processing these materials because they have a very big effect on viscosity. Could you elaborate for me how you incorporated temperature? Do you assume one constant temperature in the polymer always? How realistic is that? What are your heat sources for temperature, and how do you accommodate the different types of materials which are in your print head?
The esteemed opponent, I might have to ask you to ask the question again because I'm not sure I heard everything perfectly.
Okay, I will raise my voice a little. So in the model which you made in chapter 2, how did you account for realistic temperatures? Did you assume that the polymer is at one constant temperature throughout? What did you consider as sources for heat in your print head and or material? Basically, how did you model temperature? Is it just a measurement you did a rheology curve for 3 different temperatures and you fed that into it, or is there more to it?
Highly esteemed opponent, thank you for the question. Now everything is clear. Yeah, so first of all, considering I started by getting acquainted to the machine that I had. And one important thing I noticed at the very beginning was that there was no homogeneous temperature distribution. So all of my measurements at those times were biased by inhomogeneous temperature gradient. So therefore we did work at first by making the machine itself more reliable. We actually built second heater to be applied at the nozzle area, that is the area that is most subjected, as confirmed by your PhD thesis. That's the area that is most subjected by high thermal gradients. So we developed an external heater to keep the temperature in that area constant and be able to assume that the material is all at the same temperature. So for the practical part we did this, and therefore from that point we moved on by indeed assuming that in all these processes, at least those that take place inside the printer, such as flow development and therefore the calculation of the final flow rate, we assumed that the process was an isothermal process. Then another assumption we made was that right after the position of the filament of the fiber making the scaffold, we assumed that there was no influence whatsoever of the printhead, while instead we know that in some devices that cannot be assumed. There are some devices where you have an enclosed printed chamber where you can actually set the temperature, and in that case the dissipation of heat is very low, and the temperature, the heat coming from the printhead itself has an impact for sure. One of my paranims actually worked on this, and it took this into account to develop printed objects where this was actually exploited to develop crystallinity.
Okay, thank you. In chapter 1, you make a very strong statement that without your models, every time you start a new material, you need to spend a lot of time empirically setting parameters. I'm wondering, the models you have developed, to what degree have you actually solved this? With how much have you reduced this empirical lead time?
So at the moment, I think the only person who was freed of this burden was myself. But in my mind, as mentioned, this model would be a black box in a piece of software attached to any printer controlling software. I would like that to be. I also have other ideas on further developing this model by, for example, attaching a torque meter to the screw acting on the printer, so that depending on the torque to be applied, we would know the real-time viscosity, and from that we could actually input that parameter without having to run rheology inside the model and having a sort of feedback loop, so that to be able also in case of printing materials, thermosensitive materials whose viscosity might change over time because of degradation, we would have an inline monitoring that would allow us to adjust the printing parameters over time depending on the current exact material properties.
Okay. Allow me to skip to chapter 3. I apologize for rushing, but my time is limited. I want to talk about the tensile testing you did in chapter 3, specifically figure 1 on page 82, where you have the 4 tensile curves and also the complex viscosity curves. The methodology you used for the tensile testing, you went relatively fast. You took 6 millimeters per second to determine modulus. That's fast. So is there a reason you chose that speed? Could you also tell me how you determined yield strength?
So you're talking about figure 1, subfigure E, right?
Subfigure D and E and the methodology behind it, yes.
I use tensile testing for developing this plot. I made dog bones.
Yes, but you used a relatively high speed, testing speed, 6 millimeters per second. Is there a reason you chose this relatively high speed?
So in all honesty, at the time, I didn't know much about mechanical testing. So I just referred to colleagues that were more into the topic than me. And I was suggested this because we were actually more interested in the following behavior. So like not really the very first points, but to see, considering that plasticization is known to increase ductility of materials, at first we were kind of worried of by keeping pulling the specimen without having reaching failure. So we decided.
Speaking of ductility, apologies again for moving ahead, but speaking of ductility, you see a very clear embrittlement for your higher concentrations, which also correlates to significant viscosity drop, but I find no discussion on this in the text. Could you make a link between these two occurrences? So the embrittlement, does it have a link not just with the amount of plasticizer, but also with the different flow behavior?
So we know that the plasticizers work by placing themselves between polymer molecules. If I'm not mistaken, what I stated in the text is that having excessive plasticizer might actually reduce the number of entanglements between the polymer molecules and therefore giving specimen that break earlier.
Thank you. I have one final question, if the chair will allow me. You work with PLA types who have a glass transition temperature of 50 degrees. And in the end, these are meant to be put in the human body, which is at 37 degrees with a long time static compressive load. How do you see that? Could you look ahead towards potential creep behavior of these materials?
Highly esteemed opponent, I might have to ask you to repeat the question again because I didn't hear very well.
No problem. So the materials you work with have a glass transition of around 50 degrees Celsius. These scaffolds are intended to go in the human body at 37 degrees, which is relatively close, and also under a long-term static compressive load. Would you be able to look ahead for me to potential creep behavior of these scaffolds in the human body?
So we also know that water can work as a plasticizer itself. So I'm worried by the fact that over time, and also we know that in case of amorphous polymers, water penetrate the bulk of the material more easily than with semicrystalline polymers. We know that crystals in semicrystalline polymers are harder to be penetrated by water molecules. My fear when using amorphous polymers for such applications is that over time, besides hydrolysis, and we know that PLA is subjected to hydrolysis and that temperature also speeds up the process. So besides hydrolysis, I fear that indeed water might further promote and speed up the degradation process, but not the chemical degradation process of the material, but the degradation process of the implant as well, also from a mechanical perspective. Okay, so
this is all very correct. My question is on the mechanical phenomenon of creep, not on the chemical degradation.
We have to continue the opposition with the next opponent. Sorry for that.
Thank you.
So the opposition will be continued by Dr. Lawrence Hawke, expertise in molecular rheology from Maastricht University. He was also a member of the assessment committee.
Thank you, Mr. Chairman. So, dear candidate, I would also like to stress that I enjoyed reading your thesis. So my questions now are, so first of all about chapter 2, first question about the modeling. Is there, I didn't quite understand is if there is a continuity in your model, because you treat the extruder in 2 steps, the screw and the nozzle. So do you take as the initial or boundary conditions for the nozzle the output from the screw or not? Like, for example, the temperature and the stresses. This was not so clear when reading the thesis. So this is the first question.
Esteemed opponent, thank you for your question. Yes, there's the continuity. I actually used the continuity theorem, if I'm not mistaken, that should be the name. So basically, the development of the equations for the calculation of the flow rate out of the nozzle was based on the fact that the flow out of the extruder part, so out of the zone with the screw, was equal to the flow entering the nozzle, and that's actually quite widely used assumption, because also in other works and mainly in other books, this was like a principle, a prerequisite for any kind of modeling of this type. So indeed, I don't assume any loss in mass, any loss in flow, any loss in material when going from the extruder part to the nozzle. And what's very important that I want to underline is that you cannot run any type of analysis and modeling on the nozzle itself if you don't take into account what happens in the extruder area, in the area with the screw, because all the shear stresses, the shear rate, and so on, but also especially also the viscosity as well, because in my model I'm not modeling a Newtonian flow, therefore viscosity depends on shear rate, and therefore the viscosity of the material inside the nozzle is highly dependent, of course, on the shear rate, which depends on the velocity profile of the material at the exit of the extruder. So I had to put these 2 pieces together to have an interdependent modeling between the 2 parts, and in fact I could not solve anything analytically, but I had to apply numerical models.
Okay, thank you. Now about the viscosity. So you are performing characterization of the material using linear rheology. If you go to higher shear rates, do you think that this characterization will be adequate, or you need to do some extra characterization in order to optimize your viscosity function?
Esteemed opponent, thank you very much for the question. That's a very good question. I had a lot of doubts about this. To answer my doubts, I had to run computational simulations, because there was no way whatsoever of understanding from outside the shear rates involved in the extrusion process, and also the deformations involved during flow in that case, and therefore, yeah, that was a prerequisite to understand in what kind of rheological measurements I was supposed to do, if small amplitude, high amplitude, or whatsoever. I had to run computational simulations to understand the kind of shear rates involved in the extrusion process, and I noticed, but also, and this was confirmed by literature as well, and I noticed that they were lower than expected, because yes, it's true that the equipment compared to industrial extruders is much smaller, which actually could, at the same pressure, would give higher velocity profiles and therefore higher shear rates. But of course our pressures are much lower. The torque involved to move the screw is much lower, the speed of the screw is tendentially lower, and so on. So all in all, the computational modeling via finite element modeling told us that everything could be, the small amplitude rheology, for example, was a good test for characterizing the material that could mimic properly the actual behavior in a real situation.
Okay, thank you. Now about chapter 3, and again, rheology, you have you plot the complex viscosity as a function of frequency for the various blends, so the amorphous material, the PLA, and then with vitamin T as additive. Is there an error bar in those curves? I mean, do you report an average of several experiments, or it is just, let's say, one experiment?
That was also a great point of discussion during those times. So coming from the biology side, where everything has standard deviation, I was a bit unfamiliar with how to present data in this case. That's not the result of only one run, so it's definitely reproducible, okay? But apparently I was told by colleagues, experts in the field, that the habit is to plot these results with, let's say, a descriptive curve. So with no error bars or whatsoever. But for sure, what I want to assure you is that those data are not the result of only one single measurement.
Okay.
I ran the test several times and I took just the curves that looked the best, not in terms of values that I wanted, but like, I don't know, maybe more linear and less wobbly, because, you know, especially in a rheometer, which is a very sensitive piece of machine, sometimes you might have a point that goes a bit off, because, I don't know, even vibrations on the floor sometimes might affect your measurements with a rheometer.
Fine, great. So last question is about the chapter 4, about the microporosity. It's not my field, but what I could not, let's say, understand when reading the thesis is why it is so important to have interconnected microporosity, interconnected pores. This I didn't understand. So, and why this does not jeopardize the mechanical properties of the scaffold. Could you please give more details about this?
Esteemed opponent, thank you very much for the question. It's a very good question once again. So the role of our microporosity was not only related to mechanical properties, but also to cell population of the scaffold itself, okay? At the moment, how does it work? Like, for example, unlike biological printing, bioprinting, where the cells are embedded in the material, and therefore the moment you print a scaffold, they're embedded in the material, and they start growing from within the material. What happens with synthetic thermoplastic polymers is that basically cells are seated on the surface of the fibers making the scaffold. And they proliferate as long as they have room, and then they keep proliferating the moment the material gets degraded by the body, okay? And depending on the specific polymer in use, this can be bulk degradation, surface erosion, or these are two different processes that depend on the material that is in use. Therefore, cell growth goes in parallel with scaffold degradation. And we know that some synthetic polymers may take, if not years, for sure months to degrade. Therefore, we wanted to have also something that could be to increase the surface area available to cells, okay? So to increase the amount of cells that could adhere to our scaffolds, the amount of cells that can be generated by proliferation without having to wait for the material to degrade. And that's one thing. Another thing is to promote the inflow of nutrients and outflow of waste products. So having these pores interconnected not only with each other but also to the surface was a prerequisite to obtain all these properties, because if you have a pore that is there, fine, but that is not reachable by anything, it plays a role for sure on the mechanical behavior, but it's completely useless from a biological perspective, because it cannot be reached by cells. It cannot be reached by cells mainly, and that was actually our. We had so many for this chapter. We had so many objectives to reach with only one single strategy, and that was actually the goal of this chapter. And the answer in biology is just there: spongy bone. Okay.
Thank you very much. To interrupt here again, sorry for that. We have to go on with the opposition. Thank you, Dr. Lawrence, for your questions. The position is continued with Professor Patrick Anderson. He is a chair in polymer processing and performance in the Technical University of Eindhoven, and he was also a member of the assessment committee.
Okay, thank you, Mr. Chairman. First of all, dear candidate, my congratulations with the thesis. Beautiful front cover. I will not ask questions about it. I will ask some questions on the equations on the back in a moment. First, I would like to go to Chapter 2. In Chapter 2, you go through your model, and then you present some simulation results. Well, I just want to go to one of the figures and maybe have a short discussion on this. So I would like to go to Figure 3, page 60.
Thank you. Figure 3, page 60. Okay.
Yeah. So if you look at the results you have, you're plotting mass flow rate as a function of screw speed, and if I look at the effect of the temperature, we get nice lines. They're just linear lines, and the slope is changing. And well, I think I understand why. If we then go to Figure D, where you're actually also looking at the effect of different temperatures given one pressure, then if I look at the bottom curves of 180 degrees, and I put a piece of paper to it, I see that the black line is not a straight line anymore. The slope is changing a little bit. And I would like to ask you if you can show me in the equations where this apparently nonlinear behavior is coming from.
Highly esteemed opponent, thank you very much for the question. Just give me a minute. It's a bit hard for me at the moment to point at the exact equation, but I can explain you.
Yeah, just a physical reason why.
Yeah. So if we were talking about a Newtonian polymer, there wouldn't be this. It would be a straight line. Okay.
Okay.
I actually made this model. The very first version of this model was for a Newtonian fluid. And there was definitely a straight line between flow rate and screw speed.
Okay, so if I summarize, you're saying for the higher screw speeds, we're going into a regime where shear rates are higher, and then viscosity goes lower, and that's why we get this.
Yes, but it's a bit more complicated than that, because inside an extruder there's also something called a backdrop pressure. That is basically a pressure that decreases the throughput, because so by accumulating polymer at the outlet of the extruder, you accumulate polymer there, and a pressure is originated because the screw works as a pump.
Yeah.
So you have an increase in pressure due to the screw action from the entrance of the extruder till the end.
But you also have that Newtonian fluids.
Yes, but from my simulations and also from my calculations, the polymer that I used was mainly in the Newtonian regime in most of the areas of our printer. It was just a little bit on the transition region.
Okay.
It was never on the hardcore power law region, okay? So it mainly behaved as a Newtonian fluid.
So you're saying that the characteristic shear rate which you have is really in the Newtonian regime and it's not in the nonlinear regime?
I would say so, or if not, it's just at the edge of the transition. It's on the transition region between the Newtonian plateau and the power law area.
Okay, thank you. Let's go to one of your equations on the back. So in chapter 4, page 104, this equation 4, you describe an equation which can give a critical capillary number which can tell something about what will be an effective drop size. And I looked at what you wrote down, and then if I go down to the results on page 122, there you say, well, what we see is that the predictions are really smaller than the droplets we see. And well, it's apparently it's big enough that you notice it. So is there something wrong in the experiment, or is the model not complete, or do we need more equations?
Highly esteemed opponent, thank you very much for the question. That's actually a very good question, because the modeling that I did in that chapter, that comes basically from the work of Utraki, I really enjoyed its book. It explains the...
Yeah, I know the book.
Okay.
I also know the person, so it's okay.
Oh, okay, perfect.
Yeah.
So these equations come from a system with only one droplet, okay? In these equations, the potential coalescence between droplets is not taken into account, and that's why in the results I stated that the predictions were giving way smaller droplets than the ones that we got. Also, those equations were not taking into account the presence of a third phase, such as sodium citrate.
Okay, are you saying that it's acting like a surfactant in a way, or is it changing interfacial properties, or?
No.
So this relation you have, it's only valid in shear.
Yes.
Huh? So if we now add also the fact that also elongation plays a role, does that matter? Well, does elongation play a role or not?
That plays quite a role.
Yeah,
the problem is that I don't think we had a quenching fast enough to notice the effect of elongation, because, for example,
I'm not sure. So if you, in this result, you see that for the viscosity ratio is larger than 4, you don't get any breakup of droplets. In elongation, actually, you get breakup over the whole complete range, which means going automatically to smaller droplets.
Yeah, that's for sure an effect of elongation. What I was saying is that, because that's actually something, a road we wanted to explore, to print at much higher deposition rates to indeed see the effect of elongation. And actually at first, before even thinking about sodium citrate, we were thinking about using just a two material blend system to exploit the effect of elongation and obtain kind of tunnels, regular tunnels inside the fibers. But what we noticed is that yes, there was an effect of elongation, but our quenching after deposition was not strong enough to preserve those long fibers.
Good. Thank you very much. I have a bunch of questions, but I'm going to give some time to the other opponents. Thank you.
Thank you very much. And we continue the opposition with Professor Roman Truckenmüller. He's a chair in microtissue engineering at the Merlin Institute. He was also a member of the assessment committee.
Thank you, Prorector. Dear candidate, let me also congratulate you on your thesis, which I very much enjoyed reading and where I also learned many new things, I have to say. But let us go straight to the questions. My question 1 relates to chapter 1 and 2, and I was wondering actually if your model can also be used, for example, to make the machine doing an online kind of adjustment while it prints. For example, if you imagine there might be a camera resolving your fiber diameter Would that underlying model be able to permanently make small corrections, for example, vary the temperature up and down or the screw speed?
Highly esteemed opponent, thank you very much for your question. That's actually one of my dreams. I thought often of including my model into a machine that could actually self-adjust. I already saw in literature that there are systems based on cameras that evaluate the final, for example, fiber diameter, and then give a warning to the user or change the deposition parameters by themselves, but still in a trial and error, according to a trial and error approach. So basically assume, like, I don't know, the fiber is too thin, means the head is moving too fast with respect to the flow rate. What do we have to do to reduce the speed of the head? In the papers I read about this topic, basically what they do is that, okay, they have the camera, sends a signal to the machine, and the machine step by step, I guess there's a PID controller, the machine step by step slows down, but it doesn't have like a reference value to target, a reference target value, okay, as the implementation of my model would give. So your solution is definitely what I'd like to see on the market one day. I don't think there's any, and my model can be definitely entered the workflow.
Okay, thank you very much. My question too would be, again, related to chapter 1 and 2, sort of a next escalation step. So if the polymer is sort of unknown and you just would fill it in your cartridge, would you be able, for example, by continuously maybe increasing the temperature, at some point maybe the material would be able to outflow, leave the nozzle, would you be able to make test prints, test structures, and at some point also understand what polymer you have? Because in principle you have a sort of measurement device. You can adjust pressure, temperature, you know the position, you can differentiate, you know the speed, the acceleration, you might know the torque, the current. So you have sort of a measurement device, and you can make maybe print test structures, look on the sagging. So again, if a camera would be there, the only thing what would be added to the machine, and maybe the machine would be calibrated, could you use it to also sort of characterize, so you would maybe not even do something like a rheology measurement, because you would do the rheology in a printable range, you would just look what you printed, how that looks, and would that be possible?
Highly esteemed opponent, I would say yes. Those are actually thoughts that are beyond what I've been considering so far. But yes, consider also the fact that when it was time, I think what we have to do this moment is to actually readjust the machines we have to adapt to the polymer we must use, okay? We cannot run away from those polymers, okay? Those are the prerequisite for printing our scaffolds. What we can change is the manufacturing process. The chair, Professor Ragaert, herself in her PhD thesis developed. She used this very same machine we did, and she changed completely the printhead, taking into account the degradation process. For example, I also consider the fact of, because the problem of thermal degradation arises from the residence time in a melt, I even consider the fact of redesigning the flow channel to have like melting when I want, right before extrusion, okay, and therefore reducing the residence time, because nowadays what we have is just a reservoir full of polymer pellets that get molten, and they just stay there for only God knows how long. And so I think it's just a matter of understanding the relation between the printer itself and the material properties. So, and therefore design printers and the printhead specifically according to the current limitations. And I think that can be easily done.
Okay. Candidate, thank you very much. I'm satisfied with the answers and give back the word to the prorector. Thank you.
Thank you very much, Professor Druckenmüller. We come to the next and last opponent, Dr. Ravi Sinha. He's a member of the Defense Committee. He has an expertise in biofabrication technologies from Region Biomedical. Dr. Sinha.
Thank you, Prorector. Congratulations, dear candidate, on this nice work. I also greatly enjoyed reading this. Especially enjoyed the chapter 2, which was a valiant effort in terms of the number of physics you solved and tried to make the moving target of optimizing printing parameters theoretically move a little less. So my questions will be on this chapter primarily, and I want to see if you can simplify this model further. So in your chapter, in the table 1 of chapter 1, where you compare various printing methods, you compare, in the comparison it comes across that 3D fiber deposition and screw-driven bioextrusion are almost identical in all criteria that you evaluate them on, while the screw-driven piston extrusion could have been much easier to model. What made you choose the more difficult modeling choice?
Dear esteemed opponent, thank you very much for the question. That's a good question. Yes, considering the other extrusion techniques would have been much easier and would have made my life much easier as well. However, I think that the techniques based on screw are more precise. The control on the flow rate is more precise. And also, they develop higher driving forces. We're talking a rotating screw, so we can talk about torque. And therefore, that allows the extrusion of much higher molecular weights polymers, okay? And these we know are favorable in terms of mechanical properties, especially considering that these kind of techniques based on melting thermoplastic polymers are aimed at the regeneration of hard tissues, such as bone, as described in this thesis. Therefore, I wanted to focus on that specific class of melt extrusion additive manufacturing techniques because I believe in the level of control the user can have, especially if we consider the size, the sizes of the scaffolds that we produce. We're talking about fibers of a few hundred microns in diameter, and therefore, to print that in an accurate way, a precise control on the flow rate is needed.
Okay, thank you. The next place where I thought you could have simplified the model was the model of the nozzle. So you solved the cross viscosity model in a place where there will be such high shear rates that you could have simply used the Newtonian fluid. Why did you go for this? And maybe even use the Hagen-Poiseuille equation as a simplification. Why did you go the way you went?
Dear esteemed supervisor, thank you for the question. I decided to do that because, as mentioned previously, checking at the shear rates that were given by my computational modeling, I noticed that indeed often the polymers I used to use to manufacture these scaffolds were in a shear rate where they were on the transition region between the Newtonian plateau and the shear thinning region. So I was afraid that, for example, I had other colleagues printing with way smaller nozzles. In that case, the shear rates would just increase, and therefore the viscosity point would shift away from the transition region and most likely to the power law region. In that case, the assumption of having a Newtonian polymer, I don't think would have hold anymore. And I wanted to be precise. I mean, numerical simulations, numerical methods were needed in any case. So at that point, I decided to use them for a more complete picture of the problem.
Okay, thanks. And then one final question. So you talk about the printability window, and you say that if you measure the viscosity, the thermal characteristics using DSC, and know the machine geometry, you can work out all the printing parameters. But I did not see a conclusion whether you can find a printability window for every material, or are there some properties that will make a printability just inaccessible? And how from your model you can find these?
Dear esteemed opponent, thank you again for your question. At the moment, I would be talking about the printability window for amorphous polymers. I must say that one of the big limitations of my model is the absence of crystallinity, which really would change a lot of properties of the final scaffold, especially in on the mechanical side. And I have...
Andrea Calore, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you, and also your company, await the results of our deliberation and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. Only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. Better future than we go. And even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. South side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Can't fly by now, don't waste all your time. Cause I'll go the extra mile.
I hope I don't.
Andrea Calore, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Moroni is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I do.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Andrea Roberto Calore, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present to you with a degree certificate signed by the rector, the secretary, and the other members of the committee and affixed with the official seal of the university. Careful, otherwise. This is you, Andrea. Caro Dottor Calore, dear Andrea, what a pleasure to address you just after the recognition of your efforts and endurance of the past years working together. Together, small peaks and valleys for humans, yet giant for cells, meandering through fibers, engineered porosities, and learning together the fundamentals of material processing. We came to this wonderful day for you, for us, supervisors, and for your family and friends. Pochi ma buoni. We first interacted somewhere in the fall of 2015, if I remember correctly, when you applied for a PhD position in the group. At that time, there were several openings as the Merlin Institute just got started. You had the opportunity to select which topic to work on. At least I remember in the email I asked you a couple of different options, and chose for the ambitious project that brought today your doctoral degree. Not only ambitious for the science, we have seen clearly today how many questions, especially on the famous chapter 2 where you got, but ambitious for the team. It was the first time for many, for Merlin and the MEBME institutes to collaborate, for your supervisors to work together, and not just two, as in many cases, it happens, 5 of us. You see 4 of us here today, but together with Catherine, Carlos, and Jules, we initially had also Dietmar Aul, whom I would like also to thank for his support during his time, as long as he was here with us at Maastricht University. It was therefore not just a learning experience as a scientist, but as a manager and a communicator. It's not really easy to get 4 people in the same spot. And yet, also in these skills, you did splendidly. After the interview, it was clear that you convinced everybody. The impression was outstanding. You got the job, and we are here today celebrating yet another success in your young career. Your PhD degree. In these years, I've got to know you more and more. A cheerful, solar man with a strong sense of ownership and responsibility towards what you embark into. A fearless sense to explore the unknown. There were many unknowns here. Whether closer to your engineering training, or farther away into material science and biology, yet keeping it pragmatic and down to earth. Sometimes you warned us, oftentimes I have to say you warned us, of how difficult it was to achieve what we asked you. Oftentimes, we also had to persevere in persuading you that it would not be so difficult if we would take the limitations of the innovative approaches that you developed into account. And the fact that in many of your chapters there were also a first time for many disciplines in such an interdisciplinary field like biofabrication. Yet, that pragmatism that characterizes you was essential to keep the progress to the point and advance in a realistic manner. Then writing came. Writing is often a dangerous road, both for the students and for the supervisors, as it is always a fine effort tuning to get the right flow of a story and a blend of different styles. And Andrea, again here, confirmed himself once again for the smart man that he is. Reading your chapters was a joy, which has been crowned, it's probably not that many of you know, by the Best Paper Award from the Journal of Materials Research for his last experimental chapter, chapter 5.
Yes, thank you. Dear Andrea, it is with immense pleasure and also proud I'm taking this opportunity to express how unique I find the journey that we have experienced, the thesis, its cover, the lessons I and the supervisory team have learned from you, and your character. The prize that Professor Moroni refers to was indeed well-deserved and a result of the arguably overexpressed multidisciplinarity that your funding agency and us imposed. But it was realized by no one else but you. Thanks to this prize and Lorenzo's unavailability to receive the award in person placed me as a surfer in a very nice position. Weren't it that my kids chose Euro Disney over Honolulu? Yeah? So you were anyway part of our first generation PhD students, not only in Merlin, also at AMIBM, and you were part of a winning team because Gijs led the student team to victory at an Arlangseo student challenge. Varun got best poster prize in India, receiving the prize from Mark Hillmeyer in his wet, dripping swim shorts as he returned from the beach instead of the last lecture. But anyway, the academic excellence combined with social adventures marked the group in which you performed. It has been a joy to witness the nucleation and growth of a tight friendship, family, as you name it, in which you had a very connecting role. I would say maybe the amorphous phase. Many of my colleagues describe the amorphous phase as unorganized, but I disagree. Only based on a very profound understanding one can model it, and one can organize the unorganized. So it is a signature of who you are and what you have achieved. Organizing the vast ideas, expectations, and high academic quality in each scientific discipline is truly admirable. I wish to thank your family, your friends, supervisors, Lawrence as well, for their evidently strong support, and also the members of the Corona for their reviewing. So dear Andrea, dear Dr. Calore, it has been a privilege to co-supervise you, and I'm confident that your skills and unique character remain unnoticed. Will remain not unnoticed, neither in academia nor in your private life. So I wish you all the best in a prosperous career.
You have crowned these efforts today with a splendid defense. Let me take this moment also to thank as well the members of the committee for taking the time to read critically your thesis, in particular Dr. Lawrence Hawke and Professor Patrick Anderson from Chaos University and TU Eindhoven, respectively, as well as Ravi Signa from Region Biomedical, Roman Drucke-Müller and Kim Regertz from our Maastricht University, as well as Martin Puse, who has not been able to be here today, but was a member of the assessment committee, for taking the time to be here today with us and assessing your thesis. Let me also take the time to thank the Brightlands Material Center that also gave us the opportunity to work together with MEBN, with Jules and Catherine, as well as taking a little time to also congratulate your large and diverse supervisory team. Carlos, thank you so much for all the help that you gave us during the printing moments, at the training, beyond the training, above the training. You are a great companion in our scientific journey. Catherine, thank you so much for all the work also that you have done together with Jules in our continuous supervisory meetings, also with the other partner in disaster of Andrea, that is Vahid, that hopefully we will see also soon defending his thesis. Your support on the chemistry side of the project was always very punctual. And of course, I cannot be any more grateful to you, Jules, for indeed the wonderful journey that we had together in supervising daily Andrea. Vorrei estendere le mie più vive congratulazioni anche alla tua famiglia e ai tuoi amici. Anche grazie al loro continuo supporto sei riuscito a superare i giorni più frustranti e difficili del percorso di dottorato e grazie a voi siamo qui oggi. Andrea è un uomo con grandi valori, una squisita educazione e professionalità, grande rispetto per noi, per i suoi colleghi, sempre pronto a dare una mano in caso di bisogno. Grandi valori da voi insegnati di cui vi vorrei ringraziare di cuore. Andrea, I wish you always a clear and calm waters in front of you. You have your swimming partner of disaster also here in the room. I know that when storms will come, you will be well equipped. I hope that our routes will still cross in the future, whether you are swimming towards new professional goals or in the sea. We will be there for you. It was a great journey.
Thank you.
Dear Dr. Calore, also on behalf of Maastricht University, I congratulate you with the degree you have acquired. I also would like to congratulate, of course, your family, and also the supervisory team, greatly presented here already by Professor Moroni. I would like to share a couple of comments that we just discussed in the little room over there. You're very critical. You have a good grasp of your work and of your limitations. You did a very broad work, and you have a very good conceptualization, which is not often. You do not go hurdles out of the way. And chapter 2, the famous chapter, was groundbreaking, and also your supervisors learned a lot. So I really wish you a magnificent future. But for now, enjoy really this fantastic day. Herewith, I close the ceremony. This was the official part. I would like now the audience to go to the rafter. Then we go to the stairs, make another picture there. Then we return to the rafter, and you can still not congratulate Dr. Calore, because